this afternoon's session from Gabriel Valiente from Catalonia. He's going to talk us about tripartitions and phylogenetic networks.
Okay, so thanks a lot. It's a real pleasure to be here. Actually, you're supposed to see on the left index of the talk. It's a little too dark, maybe. But there are essentially, after some motivation slides, or two parts of the talk. One is previous work on tripartition metrics, and then the second part of the talk is a new class of phylogenetic networks that we call three-child networks. So this perhaps a little better. So first will be just a review of some basic notions. Then different attempts, previous attempts to define a tripartition distance for phylogenetic networks. And then all the notions as results about three-child networks. Then some slides and some, hopefully some web demo of tool support for these networks and a brief discussion. So, well, essentially, it all started with a vision of Charles Darwin of explaining the evolutionary history by means of trees. And it turned out that the trees are not enough to explain many evolutionary scenarios. And you are maybe all familiar with these pictures of Doolittle's work. And there are even several papers showing that by just changing slightly some parameters of the phylogenetic reconstruction methods, you can get quite different trees. And most importantly, if you want to cover also some evolutionary processes that act not only at the individual but also at the population level, then you have to deal with recombination between genes, hybridization between lineages, and homoplasy, also lateral gene transfer. And so this is where the evolutionary history can no longer be explained by a tree, and you need a graph or a network. So this also well-known classification of all this world of phylogenetic trees and networks. And for the purpose of this talk, I will try to talk in the most general sense possible of phylogenetic networks, just as rooted, directed acyclic graphs, and distinguishing between tree nodes and hybrid nodes. So the tree nodes are those that have either none or one in common age, and the hybrid nodes have at least two in common age. And then the leaves of the tree will be budgeted labeled on some finite set of tags or species names. Okay, so far so good. So this is an example, and in all the depictions of phylogenetic networks, I will be using this convention. So the tree nodes are depicted as little circles. The hybrid nodes are squares, and the arrows are supposed to go always top top down, or also horizontally from the tree nodes into the hybrid node, like here in the middle. So like this hybrid node, these two arrows will point here, and this recombination event or hybridization event. Okay, so this hybrid node represent all these non-tree-like evolutionary events like hybridization, recombination, or lateral gene transfer. For instance, in recombination, we have a coalescent node, then two species, and a recombination node, which is the hybrid node in the network. Or in lateral gene transfer, it could also be understood in this way, as in the same context as a hybrid node representing the lateral gene transfer event. We will also make a distinction between strict and non-strict descendants. And this distinction is new for phylogenetic networks. You don't need to do it in phylogenetic trees, but it will be important here because it will capture the information, topological information about the relationship between hybrid nodes. So first of all, the cluster is the usual notion. The cluster of a node is the set of leaves that are descendant of the node. And then we also define the strict cluster as a set of leaves that are strict descendants. Here, strict descendant means that every path from the root of the tree to a leaf goes through that node. So there's no alternative road to a leaf. And I'm talking about a root because these phylogenetic networks, in the most general sense, could have more than one root. This is usually not the case, or might not have much biological meaning, but from a mathematical point of view, there's no point in enforcing this constraint. Then the alternative to a strict cluster is a non-strict set of descendants. These are all the leaves that are descendants of the node, but for which there are some path from a root that doesn't go through that node. Okay? And then there's also the non-descendants, all the leaves that are not reachable from a given node. So for instance, here we have the same phylogenetic networks as before, and now we have here computed the set of the cluster, the strict cluster, and the non-descendants. Sorry, the strict cluster, the non-strict descendants, and the non-descendants. These are A, B, and C complement. For instance, for this line that I highlighted here for the G node, we have only one, all the paths from the root here to the leaf number 4 go through node G. So 4 is in the strict cluster. Now 2 and 3, for 2 and 3 there are some paths that go through G and some paths that do not. So it's 2 and 3 are non-strict descendants. They belong to this B set. And 5, for 5, there's no path, 1 and 5, there's no path from the root to 1 and 5 going through G. So these are the non-descendants. Okay? Now, with this definition, phylogenetic tree turns out to be just a phylogenetic network where there's no hybrid nodes, and therefore the clusters are all strong clusters, and there are no all the non-strong the set of descendants are empty for all the nodes in the tree. Now, for trees, there's also the well-known notion of bipartition, which was already mentioned a couple of times yesterday, that for each edge of the tree, we have a split or a partition into two sets of leaves, those that are descendant, belong to the cluster of the tree, and the other ones. And the bipartition of the tree is just a set of all these splits or bipartitions. For instance, here, for this tree, we have this bipartition, and usually you don't care about the bipartition, the trivial ones on the bottom that are defined by the leaves, so I put that only for the first time. And usually what you want is to see the bipartitions of the internal non-root nodes. This was, to my knowledge, the first time it appeared, it was used to define a metric on phylogenetic trees, was in the work of Michel Bouc, 1978, and then the well-known Robinson-Fall metric, which defines a bipartition distance between two phylogenetic trees as just the size of the symmetric difference of their cluster of the set of partitions. Okay. So, for instance, for these two trees, they have apparently they have the same topology but different labeling of the leaves. If we compute the cluster representation, the clusters do not agree at all. They are all different. So the distance is equal to 8, the size of the symmetric difference of the two sets. There are some versions of this metric where the symmetric difference is divided over 2. Now, what you want for any distance between trees to be a true distance, in the sense that it satisfies all these properties, usual properties that you ask for, that allows you to search in a metric space, like non-negativity, separation, symmetry, and triangle inequality. So non-negativity and symmetry are usually very easy to get. The triangle inequality is it's not always essential, because there are also some ways algorithmic ways to search in a quasi-metric space. But the real important property here is the separation, because it's the one that defines a real distance that allows you to tell apart different phylogenetic networks. So when we go from trees to networks, then we need to enrich these bipartitions into what's called tripartitions, which are just the sets of these three components, which are the strong descendants, the non-strong descendants, and the non-descendants of each node in the tree, in the network. Okay, so it's like a bipartition, but now we have three components. So, for instance, in this case, I've already shown the tripartition. So it's this for each node, also discarding the leaves, which are trivial. We have these sets of strict, non-strict, and non-descendants. So then there's also, in the words that I will briefly review afterwards, there's also several previous attempts to enrich this tripartition with some additional information, in the hope of being able to show these properties I reviewed before of a true distance. One is the B-weight tripartition, where the leaves of the network are weighted with a maximum number of hybrid nodes in a path from the node to a leaf, or also the A-B weight, where the set of strict descendants and non-strict descendants are weighted. So, for instance, in this previous example, we will have these weights. If we weight only B or A and B, so the sub-index here is the number of paths. The number of hybrid nodes that you found in these paths. So, obviously, for a tree path, a path containing only 3 nodes, these sub-indexes are 0. Sometimes we just drop them. This tripartitions captures essentially topological information about the network, and then it allows you to define a tripartition distance, which is just like the same as bipartition, but for networks. So it's also the symmetric difference of the set of tripartitions for each node of the networks, but now the symmetric difference is understood between multisets. And you can also define the same for B weight and AB weight tripartitions. And if you can, these are more constrained forms. So if you can prove that the separation property of the true distance holds for the more constrained case, then it also implies that it must hold for the B weight and for the M weight tripartitions. Okay, now these tripartition distances were studied in a series of papers that revolved around the PhD work of Nahle in the Tandy Warnock's group a few years ago. And so this was, I think, the very first paper, if I'm not wrong. And there they defined the phylogenetic network with a condition that, well, several conditions. This will be a very rough presentation of, there are some more technical conditions there, but essentially that every internal node in the tree has to have at least one tree child, so cannot have all the children hybrid. And then there are some conditions that forbid these two situations that are depicted here. That a node, the red arrow is showing to the left that U1 is a parent of U2 or the other way around. So these two nodes are not allowed to hybridize into U, or a similar situation with in two different parts of the network. And then a network is called of class 1 when each hybrid node just has at least one parent. That's not a tree node. So these are all technical conditions that are imposed in order to guarantee some these distance properties of the tripartition metric. And please bear in mind this first part, that internal node tree node has a tree child. I will show later that I think that in all these works the authors have moved around the right notion, but almost, not quite. So I will show that if you add something else, that not only the internal tree nodes but also the internal hybrid nodes have a tree child, then this will be enough with some further conditions to define not only a tripartition distance but a lot of other things. Okay, in this case, in these papers they prove that they claim that the separation property holds in this case, but unfortunately this is not the case, and we found some pairs of non-isomorphic class 1 phylogenetic networks with the same class of with the same sets of tripartitions, even weight, even in the more constrained form, AB weight, like these two ones, where I put in red the only change between the two networks, and you can easily check that they have exactly the same sets of weight tripartitions, but they are clearly not non-isomorphic. So this is not enough to separate them. So I don't know if the authors noticed that at that time or not, but then there appears several more constraints on these networks. This all about the same time, 1 year later, and where they define convergency, and they define an additional condition, and again calling this networks class 1 if they have no convergent pair of nodes. And again, this is not enough to, they claim that it's enough to separate phylogenetic networks in this class, but it's again not the case. Here we've shown that two non-isomorphic networks within this class that have instead of a tripartition distance, error rate, non-zero error rate, which is just a normalized version of the tripartition distance. And well, this is getting a little more complicated. This is the first and this is the second. You see there's only this change here, and some relabeling of the leaves. And again, you can check that they have the same set of tripartitions and the same error rate, but they are non-isomorphic. So this convergence, the next step was the introduction of what they call reticulation scenarios. And the reticulation scenario of a hybrid node is just a set of cluster of its parents, and a tripartition is enriched by adding this reticulation scenario to each arc network, to each arc with head that vertex, that node. For instance, if you have here for each of the two hybrid edges here, let's say this E edge from U1 to V, you have to add the cluster together with the tripartition with these three threads of strong, non-strong, and non-descendants. Also add the cluster of the parents. And well, there are some more technical conditions, but essentially they again claim that that it's enough to separate phylogenetic networks in this class, but again, this is not the case. Even in the enriched tripartitions, you can find in this example these two networks which are non-isomorphic but have the same set of enriched tripartition and fulfill this condition of reticulation scenarios. Then it comes the PhD thesis of Nachle, where he defined for the first time a three-sibling network, where the additional condition is that each internal node, each hybrid node needs to have at least one sibling, tree node. And again, well, there's no correlation between non-convergence and tree sibling. There are examples in both directions showing that this one doesn't imply the other. And again, in his thesis, he claimed that the separation property is satisfied in these class networks. But again, there are non-isomorphic three-sibling phylogenetic networks, which have the same set of enriched tripartitions, like this one and this one. So next comes this paper about the same year, where they again use the notion of convergency, but now for two or more nodes of a network. When they have the same cluster, now it's a different notion of convergence. And also reduction procedure, and then after this procedure, a network is reduced if it doesn't have any subset of convergent nodes. So reduction is a process, iterative process of removing convergent nodes or convergent pairs of nodes. And well, there are some more conditions, but to go briefly, this is the class of reduced reconstructible. They also introduce a distinction between model and reconstructible phylogenetic networks. And they claim that the separation property is satisfied here, but again, this is not the case. So these two networks have the same set of enriched tripartitions. They are both reconstructible, reduced, but are non-isomorphic. And then so now this why we thought that the problem wasn't trying to add more conditions to the original definition, but to revise the original definition. So instead of tree sibling, what we propose here is to define a tree phylogenetic network as a tree child. So every internal node, not only, as I said before, not only the three internal nodes, but also the hybrid nodes, must have at least one tree child. So it's like coming back to the original definition of class 1 network, but with this change. So from the biological point of view, the justification or the meaning of this condition would be that every non-extant species is asked to have some descendants, a direct descendant through mutation alone. So it's not very restrictive from the biological point of view. And here you see the difference in this example. To the left you have a tree-child network, and to the right a tree-sibling. So this is not the one to the right. So tree-sibling is actually more general, and this perhaps the problem with these previous works, that they try to model in a too general sense phylogenetic networks, and then the model was so general that it wasn't constrained enough to define a meaningful tripartition distance. So here you see the internal tree node painted here in red has both children hybrid, so this is but has three sibling nodes. Has a tree sibling, so it's tree sibling but not tree child. So what's the meaning of hybrid nodes here in this setting of tree-child networks? Well, they can, as I said before, they can represent recombination events. So they produce a new individual, which is represented by the only child, if they have only one child. And if they have more than one child, so it is usually a constraint that in most works on phylogenetic networks, that the hybrid nodes have only one child. But if this is the first scenario, the second scenario would be that you have two or more direct descendants, children. This could correspond to a hybrid individual that hybridizes before undergoing some speciation event. And this reportedly supposed to be not very usual in real life, yes.
Just wondering, By tree child, you mean a direct node that's a child node that's a tree node, or do you mean there's a path down to some?
No, a direct descendant. Some direct descendant must be a tree node. So I will come back to that later on. So just hold on for a while. So just think that if we call these tree nodes were called today normal nodes in Wilson's talk. And the point that you have a tree child, some tree child, allows you to find some path of tree nodes down to a leaf. So these networks are normal in the sense. So okay, so what do we know about this network? So first of all, some bound of the size of the network. So if we start with n leaves, and if we forbid elementary paths, so degree 1 tree nodes, because otherwise the network could grow as much as it want. If you set a maximum hybridization degree, so the maximum in degree of the hybrid nodes, let's say m, then you can have at most n plus 2 times n minus 1 plus 1 nodes in the network. And there's a similar formula playing with the sum of the degrees of all the hybrid nodes. And this bound turns out to be tight. So if you start from a comb-like tree with the root and with the nodes shown in green here, and then you add n minus 1 hybrid nodes, this here, this for n equals 4, and then each of the paths from each of these original paths, you split it by introducing m minus 1 tree nodes and connect them in this way. You get this hybridization degree m in all the hybrid nodes, and you have exactly this number of total nodes. So this nice property that the size is bounded by n times n, about n times n. Then there's another nice property is that the cluster representation is enough to characterize these tree-child networks with an additional condition. Essentially, the first condition that I talked about in class 1, which was a part of it, the first part of it is a weak time consistency condition. So in the sense that two of these networks are isomorphic if and only if they have exactly the same cluster representation. And then this entails that the bipartition and the tripartition and weight or weight theta b or ab will satisfy the separation property. With the only additional condition that the parents of each hybrid node cannot be connected by some path. And this allows us to define a tripartition distance and also bipartition distance on this class of networks. See, it's a subclass of the tree-child networks where the parents of no hybrid nodes are connected by some path. Now, time consistency has been, in the slightly stronger sense, has already been studied by Baroni, Semple, Steele, and showed to be equivalent to the existence of a temporal representation of a phylogenetic network, in the sense that you're able to assign times in some discrete molecular clock to the nodes of the network in a way that increases strictly with the tree edges and allows the parents of each hybrid node to coexist in time. So to have exactly the same time stamp. So for instance, these two networks are tree-child, but they are not time consistent in this sense. And in this case, this is a counterexample. So here, this to show that the weak time consistency is important to ensure that the tripartitions do define a true distance on this class of networks. So for instance, the one to the left, well, here you have these red arrows showing the difference between the two, so they are non-isomorphic. And if you try just to show that the first one is not time consistent. So if we start, let's say we start assigning times with a molecular clock, starting 0 at the root, and increasing the minimum steps, say 1 for each tree arc. So 1, 1, then here 2, then 3. Then the least we can do here is to put the same 3, not to increase some hybrid edges. But then the parents here, A and D, cannot coexist in time. They exist at different times, 1 and 3. So we need to change this 1 back to 3. So the definition says that we want time to increase over 3 arcs, but not necessarily in unit steps. So this is still all right. And now we go on with E times stand 4, B 4 again, because this is not a tree edge. And now we have the same problem with B and B, which, with B has little b and E existing at different times, 1 and 4. And if we change back B to 4, we need to start over again, and we enter a loop here. So this shows that this network doesn't have a temporal representation. Okay, so another, apart from tripartition, so keep this in mind. So we need to add this weak time consistency to tree-child networks in order to have a tripartition distance. But the good news here is that if we don't want to do that, we still have a representation which leads to another distance, which I will introduce shortly. So first of all, what we call the mu representation, or the path multiplicity representation of a tree-child phylogenetic network, is just a multiset of vectors of numbers of paths to each leaf, from the node to each of the leaves. So for instance, here we have a network with nodes, all the nodes of the network labeled by this mu representation. So we have 4 leaves. Let's say they will be, so here, in this vector, the first component will be the first leaf in this left to right order, the second, third, fourth. So it's clear that there's only one path to each of these, only the path to themselves. And if we want to count, for instance, the number of paths from the root, why do we have this 1, 2, 3, 1? Well, to the first leaf, there's only one path from the root. To the second leaf, there are these 2 paths. To the third leaf, there are these 3 paths here. Okay? And to the fourth, there's only one path. So this is a mu representation, and it's enough to characterize tree-child phylogenetic networks without any additional constraints, and can be obtained in polynomial time. And there's a very simple algorithm. You just start with the leaves. Once you are given the network as an input to the algorithm, in order to compute its mu representation, you start with the leaves, with a fixed number of the leaves, and then for each internal node in post order or in bottom-up order, you just add the mu vectors of the component-wise, the mu vectors of the children. So this O110 is the sum of these 2 children's vectors, and go on until the root. Okay? Now, this is what I said before, that this enough to, this representation is powerful enough to capture all the topological relationships in a tree-child phylogenetic network. So it allows you to reconstruct the network from its mu representation, and therefore to test if 2 tree-child networks are isomorphic or not by just comparing their mu representations as multisets of vectors. So here's also the reconstruction algorithm, just to show this point. The easy way to do this reconstruction is to sort the set. Now it's the opposite problem. So the input is the set of vectors, and the output is the topology of the network. So we just sort in lexicographic order the set of vectors, and then starting from the top, we look for the first decomposition of this of each vector as a sum of vectors below it. So, for instance, the 1, 2, 3, 1 is we can subtract the first, so the second row, the second vector. The third we cannot subtract anymore, the fourth one, and then we get these two connections, and so on. You just the next vector to be connected, to be decomposed, is 1, 1, 1, 0, decomposed in this way as the sum of 1, 0, 0, 0 and 0, 1, 1, 0, and so on. Okay, and then in this way you reconstruct the network in a unique way. Now, we also define the mu distance between two networks, two three-child networks, based on this representation, in the same way as the bipartition or tripartition, but now it's a symmetric difference of the mu representation of the networks as multi-sets of vectors. So, for instance, in this between these two networks, their mu distance is equal to 6, because they differ in these 6 mu vectors painted here in red. And again, recall that this is a difference, symmetric difference between multisets. This not only this mu distance is symmetric on the space of all three-child phylogenetic networks without any additional constraint, but also it is a proper generalization of the Robinson-Falls or bipartition distance, because if we compute it on trees, we get exactly the Robinson-Falls metric I reviewed before. Now, more things that we can do with this network. So we can align them based on this mu distance. Let's start with two three-child phylogenetic networks, N and N prime. We just define the distance between, say, this m component of the alignment, or the distance, n small m, as the difference between the corresponding vectors. This is the Manhattan distance here, the L1 norm. And then we have a second component that tells you whether or not the nodes B and B prime are both the same type or not. So to put some penalty on aligning a tree node to a hybrid node or vice versa. And then with this notation, we can define the weight of a candidate alignment of B to B prime as the sum of these two components, where the second one is normalized over 2n. This normalization is based on some bounding of to ensure that the whole alignment will give you a normalized distance. And then assume that the first network is smaller, it's not larger than the second one. The total weight is just the sum of an alignment. It's just an alignment is just a mapping of nodes of the first network to nodes of the second one, and the total weight is the sum of the weights of the correspondences using this formula, given the alignment. And obviously what we want to do is to find an optimal alignment between two networks, that is a matching of the nodes that has the least possible weight among all possible matchings. Sorry. And then this means that it has to satisfy, to minimize this formula of the total weight, but also we need to select the best mapping among those that satisfy this formula, because this alignment here doesn't have to be unique, and we prefer those that match nodes to nodes of the same type. So map tree nodes to tree nodes and hybrid nodes to hybrid nodes. For instance, this is an optimal alignment between a tree to the left and a gold tree to the right. And the total weight is 1, because all the mappings here have a weight, are mappings between nodes of the same, exactly the same mu representation, mu vector, but the roots have different mu vectors. So we have 1, 1, 1 for the root of the tree. This is the vector of path multiplicities, and 1, 2, 1 for the goal tree. And this is optimal because the mu representation of the tree is not included in the mu representation of the network. So this is the least possible, because not included, there cannot be a total weight equals 0. So 1 is the least possible one. So now I'm approaching the end of the talk. So regarding tool support, well, there are some previous tool support. Split tree has been around for a long time now. We have split 4 with some new functionalities. T-Rex, well, there are many other tools. So these are 2 of the publicly available ones. And then there are 2 tools developed in conjunction with all this work of Nagle, Warno, Moret, and others, which are Phylonet and NetGen. And then we also developed tool support for tree-child networks in the form of a PER module and a web tool. So the PER module is already submitted to BioPER. I don't know if it will be accepted or not into BioPER, but it's written as using BioPER as part of as if it were part of BioPER. But you can download it and use it independently. And there's also some web support. Now it's when everything crashes, but let's try it. So this web support is just upon using these modules, it's a simple script that takes 2 networks. You can paste in here 2 phylogenetic networks in extended new format. I will describe that shortly. And then you just submit the networks. Here is some trivial example. And then, well, Java. I agree. Let's agree. Well, I promise you everything will crash. Okay, so one of the things you get is a display of the networks following a temporal representation. If they are time consistent, and you get the 2 networks displayed in text form, all the properties of the networks, the mu representation. Oh, it didn't so long. So you get for each of the networks, if it is tree-child or not, the network in extended NUI format. Again, the mu representation of each of the nodes, so the mu vectors for each of the nodes, the sets of tripartitions, and the same for the second network. Then you have you get the mu distance, the weight of the optimal alignment, and the textual description of the optimal alignment, and also an interactive display, which is in no way a competition to dendroscope. It's just very preliminary. It's just a small Java applet that displays the 2 phylogenetic networks, but it's an interactive and synchronized display, so that in this display you can ask for, say, click on a node, like say, click here, and then the corresponding node, according to the alignment in the other network, is also displayed. Now we click here, also in the second graph, the second network. You click on a node, and then the corresponding node is highlighted. And then you can also click, say, on maybe this arc here. You click on an edge, and then the corresponding edge and the nodes are also highlighted if they have some correspondence. Let's see what happens here. So here, X2 is mapped to X2, H1 to H1, and X2 is not a parent of H1, so only one of the edges is highlighted. Okay, this is essentially the functionality of the web tool. For the PER module, there are many other things like computing the temporal representation of a network, no distances, tripartition distance, testing for tree-child, testing for time consistency, and so on. Okay, so now back here, so much for tool support. I say I would explain something about the extended Newick format. Newick format has been around for a long time and is widely accepted by biologists and also by many software tools. But we don't have anything agreed upon for phylogenetic networks. Extended Newick might be one answer to this question, but there's not a unique format. So the first form, as used in PhyloNet, consists of splitting each hybrid node into as many nodes as a total degree has a node, like here, and then constructing the Newick strings for each of the resulting trees, and also naming them in this way, so that the whole network has a name, n equals the string, and in this string we have a repeated 3, and then 3 is defined, 3 equals the tree with 6 and in post-order 6 and 3. This one format, one flavor of the format. Another one is in which you only split each hybrid node into as many nodes as in degree has the hybrid node, and then attach all the children, all the structure that hangs from the hybrid node into the first occurrence of the node. This is used in NetGen and also now in Dendroscope 2.5, 3, 4. And because it wasn't complicated enough, we added something else. So we split into, as in the first case, as in PhyloNet, but we prefer to report the Newick string as a list of Newick trees, obviously with some repeated labels, but nothing else. Because we believe that in this way you can better use some from the software engineering point of view, reuse tools to parse and produce Newick trees, and then just merge together all the nodes with the same name, with the same label, into the phylogenetic network. But I put this because it would be interesting if in this setting, in this workshop, we could come up with a unified proposal for phylogenetic networks. Maybe instead of extended Newick, we could call it Newton, the Newton format. So as a conclusion, tree-child phylogenetic networks are less general than tree sibling, but I didn't show that on the slide, but they are strictly more general than gold trees. And they impose no temporal compatibility constraint. If you impose them, then you also get tripartition distance. The mu representation gives you a metric that generalizes the Robinson falls distance. And all these algorithms are computed in low-order polynomial time. And the mu representation induces a global alignment of the networks. This is more or less a picture now. So we start from phylogenetic trees towards general phylogenetic networks. So the first interesting constraint was the gold trees, introduction of gold trees by Dan Gatsfield. And then we have tree-child that generalize that, and tree sibling that are even more general than tree-child. But we believe that they are much too general, slightly much too general. So then we have, when we come back to this, to your question before, in Stephen Wilson's talk today, if you allow me to rephrase it a little in the terminology we use in our papers, phylogenetic network will be called normal if there is a tree path, that's a path that may start at the hybrid node but follows only 3 nodes towards some leaf. For each internal node, towards some leaf. This is exactly the same definition we've seen before, but with a different notation. And this is the theorem that Wilson's brought about before, under a simple model of inheritance that allows homoplasys only at hybrid nodes, there is a unique determination of the genomes at the nodes of the tree, of the network, provided that the network is normal. And the good news is that tree-child networks are normal. It's easy to see because it's tree-child, there's always a path towards some tree node, and you can follow this path down to some leaf. So this means that tree-childs not only have nice mathematical properties, but are also biologically meaningful, according to Wilson. So this, we don't know, some things that we don't know yet is the number of abundant, or we don't know how to count tree-child phylogenetic networks. This is only for 2, 3, and 4 leaves, just to see how fast they might grow. This is done computationally. It's not, we weren't able so far to find a recurrence describing this. The number of tree-child networks, and the number of tree-child time-consistent networks is much smaller, so for leaves goes down to 105 networks. Now, if we want to see what this mu distance or path multiplicity distance means, we did some experiment on all pairs, on other pairs of tree-child phylogenetic networks. For 3 taxa, we have this distribution of frequencies of distances. So distance ranges from 0 to 12, and as you can guess, because of separation property, the only pairs that have that are at distance 0 are the networks with themselves. So this is 66 networks we have here, 66 networks on 3 taxa, and the same for 4 taxa. We have this similar distribution, and 4,059 networks on 5 taxa, which are the only ones at distance 0 of some other networks, of themselves in this case. So there are 2 papers corresponding to the first and second part of the talk, roughly, already available in preprint form, and from the archive. And so a few words about open problems. I still have 2 minutes, I see. So one thing that we would like to do is to we encourage you to keep on thinking in this direction, is to determine the discriminating power, exactly the discriminating power of tripartitions. So where's the boundary, how general can the model of phylogenetic networks be in order for tripartitions to give you a true distance. So I've shown before that time consistency is needed for so it's tree-child time consistence, but maybe something between that and tree-sibling networks. Another thing is to find true distance that generalize the bipartition distance on tree-sibling phylogenetic networks. Not only tree-child, but going more general to tree-sibling, or not only tree-child time consistent. And another set of questions deals with reconstruction problems, which we haven't addressed yet. So to characterize the set of sequences that whose evolution can be explained by means of a tree-child phylogenetic network, and provide a constructive method, a reconstruction algorithm for this class, characterizes computational complexity, and determine, this is another open question, to determine whether this mu distance and the alignment method could be extended to the more general case, so time consistent tree-sibling, not tree-child. For this, we have a counterexample for the non-binary case, but we are not sure whether we weren't able to even also to disprove that for the binary case. It might be the case that it holds. So now, just if you let me take 1 minute more, just to make some advertisement. Next year I will be giving a longer version of this talk, so a 3-hour lecture in Lipari at the International Summer School of Computational Biology, which started this year. It will be the 2nd edition. So there will be 4 main lectures. The focus will be biological networks, so not only phylogenetic networks, but also protein interaction networks. And there will be 3 hours of lecture with biologists about viruses, network evolution, comparative analysis of networks, and then a lot of tutorials, so it's especially interesting for many of you who are PhD students. If you are Italian or European, I think you might get some credits for attending this school. This is a very nice place here in Cambridge, but let me give you one more reason why you would like to go to Lipari. Here it is. Thank you very much.
Okay, got time for a few questions. Yes.
So first, I enjoyed very much the talk. I have two questions. One is simple. So what is in your hierarchy of networks? So the most general is phylogenetic networks. What constraint this network needs to hold? And the second one. HGT, lateral gene transfer network, where you don't generate just nodes everywhere. They need to reside on a tree edge. Is it always normal? You understand? It's
Yes.
not like that. It's always on a tree edge. Is it always normal?
Well, I don't know if it is always normal.
Okay.
I guess it would be, but depends on how you encode the lateral gene transfer event. But I think it can be encoded in such a way that you get a normal network.
Yeah. Okay.
But for the first question, I guess that the answer is not far here. So I think that the most general setting is a DAG, with rooted DAG.
Time constraint.
With no time constraint. But then the problem is that it's much too general. So I think your question goes for the what's the most general network that you can reconstruct from sequence data or from distance data. So if you want to go with such a generality, you most probably won't be able to find a way to reconstruct a network. So here I was talking mostly about constraints that you add in order to define a meaningful distance, not to be able to reconstruct. But my hope is that that the methods, for instance, the parsimony and likelihood method you've been involved with for tree-sibling networks, could also be applied to these tree-child networks.
Okay, if there's no other questions, we'll break the coffee and come back here at 3:30.